Okay, so now that you've lived through the math testing experience, like I said, you can redo the problems you got wrong. Just make sure you show your work when you redo them. Turn them back in, you get up to half your points back. So let's say you scored a 70, that becomes an 85, which is a respectable score. Not that 70 is horrible, but for you guys, you have to run an 80% in this course to pass because it's a prerequisite for some of your auto courses. And if it's a prereq, you got to have a C or better, not even a C minus. Here, I can pause. So today then, to start Unit 2, we're going to start talking about fractions. To deal with fractions, you remember we mentioned that a fraction has two parts. It's one number with two parts. The top, which is called the numerator, is a count. It tells us how many we have. So just like having 3 inches or 3 cows or 3 pounds, we have 3 of something here. And the bottom, which is called a denominator, is the name. That would be like the inches or the cows or the pounds, except now it's fourths. So one of the first things we need to do is to define what a fourth is. And about the simplest way to do that is to go back to the old elementary school illustration of a pie or a pizza. Pretend that looks like a circle. A fourth means that is cut into 4 equal pieces. Pretend those are equal. Here, I'll take a little bit of the pretending out of it for you. It's a little bit closer. Call it good enough. So a fourth means every whole object is cut into 4 pieces, 4 equal pieces. Or the other way of looking at it is it takes 4 of those pieces to make one whole object. Now the 3, the numerator, is telling us that we have 3 out of those 4 pieces. We have 3 of them. Oh, my coloring is improving. So you almost stop there before I get a big head. So that's what 3/4 looks like. Now we ran into it on the first day where we had like 1/3 plus 2/5, and we said we can't add those the way they're written. We have to be able to change their name. So the first thing we need to be able to do here is figure out how to change the name of these fractions. The simplest way from this illustration is to take each slice here and cut it into other equal slices. So I'm just going to pick 3 at random here. So I'm going to cut each slice here into 3 equal slices. Again, try your best to pretend these are equal. Now, how many slices does it take to make a whole thing? 12. We had 4. Each of them got cut into 3 pieces. That makes 12. How many pieces do we have? 9. We had 3. Each of them got cut into 3 equal pieces. So 3 times 3 is 9. So now what we have there is 9/12. Do we have any more or less than we did before? No, it's the exact same amount. 3/4 and 9/12 are the exact same amount. They just look different. Unsimplified is one way of putting it. The reason that we didn't change anything was what we multiplied there was 3/3. If you think about what we just said, the 3 on bottom is saying it takes 3 pieces to make a whole object. The 3 on top is saying we have 3 pieces. In other words, that's 1. We multiplied by 1. Anytime we multiply by 1, it doesn't change the value of a number. Now it can change its appearance like we did here. This is what we call a unity fraction. It's an alternative way of expressing a value of 1. And it's used, like we saw right up here, to change the appearance of a number, but not its value. And when we do measurement conversions, we're going to use those unity fractions to convert measurements a lot. Well, here we just randomly chose the number 3. Normally, we'll have to be able to figure out what it is we're going to use to rename the fraction. So we might have something like 2/5, and we need to change it into 30/5. So the first thing we have to figure out, now that we know that we're changing it to 30/5, what did we have to multiply the 5 by to turn it into a 35? 7. So if we multiplied 5 by 7, what do we have to do with the 2? Multiply it by the exact same thing. We have to multiply by the same thing in the numerator and denominator, so that we're multiplying by that 1, 7 over 7 in this case. So 2 times 7 makes 14. So now again, 14 over 35 has the exact same value as 2 over 5. It just looks different. So if I have 1/3 and I want to change it into 27ths. Perfect. This number is going to be 9. Because 3 times 9 made 27, so 1 times 9 makes 9. Not so bad? Going the other way, let's say I want to turn this back into 1/3. Well, I multiplied the top and bottom by 9 to get it there. I can reverse that by dividing the top and bottom by 9. 9 divided by 9 is 1. 27 divided by 9 is 3. And we've already showed 9 27ths and 1/3 are equivalent. So just like we can multiply both the numerator and denominator by the same number, we can divide them both by the same number. Now here we were the ones that multiplied it by 9, so we knew we could divide out the 9. The trick often is looking at them and figuring out what we can divide them both by. We might have 48 over 60. Now remember, right before this last test, we talked about divisibility rules. What numbers can 48 and 60 both be divided by? Now the ones I always look for first are 10. How can you tell if something's divisible by 10? Ends in 0. The 60 is divisible by 10, but the 48 is not. So then I look for a 5. How can you tell something's divisible by 5? 5 or 0. Well, this ends in 0, but the 48 does not end in either one. Then, because it's simpler, I jump down to 2. Can both those be divided by 2? Yes, they can. We divide by 2. 48 divided by 2 is 24, and 60 divided by 2 is 30. Now, I can see they both can still be divided by 2, but looking at them, I find something bigger they can be divided by. Can you see it? 6. A lot of times, once you divide out one number, it's when they're a little bit smaller, it's easier to find numbers that divide into them. 24 divided by 6 is 4. 30 divided by 6 is 5. We cannot reduce any further. Now, if you saw the 2 and you divided by 2, you get 12 over 15. Then you can see both of those can be divided by 3. They get to the 4/5 either way. It's just a matter of how many steps it's going to take. If you're really fortunate, you looked at this and you saw, hey, both of those can be divided by 12, and you get there in one step. We've always had it pounded into us. You have to find that greatest common factor, like we discussed last week, that largest number that divides into both of them. That's not true. You just have to find any number that divides into both of them, and then keep going until you can't divide them out anymore. So we might have 36 out of 48. Tell me what to divide them both by. 2 for sure. Okay, what do we get? 36 divided by 2? 18. 48 divided by 2? 24. Then what? 24 does not divide by 9. 6 will work. 18 divided by 6? 3. 24 divided by 6. 4. 3/4. Not so bad? Okay. We can run into numbers that look like this. 44 over 7. The 7 is telling us it takes 7 pieces to make one whole object. The 44 is saying we got 44 pieces. So we have more than enough pieces to make a whole object. In fact, we have enough pieces to make several whole objects. So if we do 44 divided by 7, our calculator would give us something like 6.28571429 approximately. Okay. Okay, perfect. The 6 is telling us that there are 6 whole objects in there. 7 goes into 44 6 times. So you're saying you take 7 times 6 is 42. What that's telling you is that these 6 whole objects used up 42 pieces. So out of the 44, we have 2 of those pieces left, 2 7s left. And that's exactly it. Basically, it's a division and remainder. 7 goes into 44 6 times. 6 times 7 is 42. There's 2 left over. So that is 6 and 2 7s. The remainder goes over what we're dividing by, our denominator. This is what's called an improper fraction. Now, they call it improper because we don't like having the numerator bigger than the denominator. The word improper implies there's something wrong with it, and there really isn't. We just don't like seeing it that way because it's hard to visualize. It's easy for us to visualize 6 whole objects with 2 little pieces left over than it is for us to visualize 44 of those little pieces. But there are times when we prefer to have a number, a fraction, written as an improper fraction. Instead of this over here is what we call a mixed number, because it mixes fractions with whole numbers. This is called a whole number, by the way, because it tells us how many whole objects we have. So we might have 25 thirds. What's that going to become? How many times does 3 go into 25? Goes in there 8 times, right? 8 times 3 is 24. How many's left over? 1. Perfect. 8 1/3. Sometimes it is desirable to go the other way, to go from the mixed number back to the improper fraction. So here, we would have to break that 8 back up into pieces. How do we know how many pieces are in each whole object? The denominator, 3. So we take 8 times 3 is 24. That 8 whole objects is 24 pieces, plus the 1 piece we already had. That's 25 pieces or 25 thirds. So we might have like 4 2/3. It'd be 4 times 3 is 12. Add 12 to the 2 is 14 thirds. Or if we had 2 3/5. 2 times 5 is 10, plus the 3 is 13/5. Okay, so now we can convert between different forms of our fractions, and we can rename fractions. Let's take a look at our operations. So one problem we had was this, 1/3 plus 2/5. We couldn't add them because they have different names. Well, we now know how to change the name. The next step, we have to know what name to change it to. How do we figure out with 1/3 and 2/5 what the common name is going to be, the common denominator is going to be? Well, there's a few ways you can do it. One way is you can just multiply the 2 denominators. 3 times 5 is 15. In this case, 15 is the least common denominator. It won't always be the least one, but it will be a common denominator. You were always told you have to find the least common denominator? It's not true. It works if you use a bigger one. It's just you have more work. You have to work with bigger numbers for one. And then at the end, you're going to have to simplify your fraction in your answer.
6 and 4.
Yeah.
So you can multiply them to make 24.
Or you could use 12. And either way, we'll use an example similar to that. I'll show you both ways. It works out, it's still extra work to do it with bigger numbers. So that's one way we could do it. That'll always give us a common denominator. Like I said, not necessarily the least one, but it'll work. It's a common denominator. Or we could use what we were learning last week with the least common multiples, where you factored the numbers. Well, 3 and 5 are both prime. That's why you can multiply them together, and it's still the smallest one. The other way you could do it is this. You can make lists. We know that if we count up by 5s, it's going to be 5, 10, 15, 20, 25, and so on, right? So you can count up by 3s. 3, 6, what's next? First, and there's our first match right there, 15. So that's telling us that 15 is our common denominator, least common denominator here. Now I set them up vertically here because my mind likes to add vertically. I like to add down the columns. I have to change both of them to 15s. That's my common denominator. What did I multiply the 3 by to make a 15? 5. What do we have to do to the 1? Times 5. So 1 times 5 is 5. What do you multiply the 5 by to make it a 15? 3. So what do you have to do to the 2? Times 3. 2 times 3 is 6. Now that they have the same names, we combine the counts just like any other number. 5 plus 6 is 11, and we keep the same name, 15. I'm not going to waste any more time with simple fractions. We're going to jump up to mixed numbers. So if I have 3 and 5/8 plus 5 and 1/6. Well, once again, I'm going to set them up vertically here. Notice I just put the fraction on the end of the number and lined it up just like it's the last digit of the number. Because in essence, that's all it is. The fraction is nothing more than just the last digit at the end of the number. Now, I do still need a common denominator. For 8 and 6, it's going to be 24. 8 times 3, so 5 times 3 is 15. 6 times 4, so 1 times 4 is 4. So now, just like any other addition, we start on the right and we work our way back to the left. 15 plus 4 is 19. We keep the same name of 24s. 3 times 5 is 3 plus 5 is 8. So 8 and 19 24s. Now you struggled a little bit with the common denominator there. What if you had just said, hey, 8 times 6 is 48? That works. So now it'd be 8 times 6, so 5 times 6 is 30. 6 times 8, so 1 times 8 is 8. We add 30 and 8 is 38. We keep the same name of 48s. 3 and 5 is 8. Both of those can be divided by 2 gives me 19 24s. And don't forget the 8. The biggest thing I'll see people screw up is they reduce this fraction and forget to put the whole number back in front of it. Notice I get the same answer either way. It's just a little bit easier here to use the smallest common denominator instead of using a bigger one. No, it doesn't stay that simple. You guys are learning by now I always make it worse, right? Let's do something like 7 3/4 plus 3 4/5. I'm just going to start setting them up vertically instead of writing them out horizontally and rewriting them. A lot of people don't rewrite the whole numbers, they just redo the fractions. I always rewrite the whole numbers because if I keep them, just keep the whole numbers way over here, I sometimes forget about them. So it's easier for me to remember them if I bring them over. 4 and 5, common denominator is going to be 20. What's going to go here? 15, good. 4 times 5, so 3 times 5 is 15. What's going to go here? 16. 5 times 4 is 20, so 4 times 4 is 16. And we're adding, we're starting at the right, going back to the left. 15 plus 16 is 31, and we keep the same name of 20ths. What's my issue here? It's an improper fraction. I take 20 out of there how many times? Once, with how much left over? 11 20ths. So 31 over 20 is 1 and 11 20ths. Now, just like with any other addition, I'm going to keep the part that stays in that place value. This is the fractions place, so I'm going to keep the fractions, 11 20ths. I'm going to carry the whole number, the 1. 1 and 7 makes 8, plus 3 is 11. 11 and 11 20ths. So let's try this one. What's my common denominator going to be? 8. Sometimes one of the denominators is your least common denominator. Here, the 7/8 is going to stay 7/8. To change the fourths into eighths, I had to multiply by 2. So 3 times 2 is 6. So now tell me what to do. So 13/8. One and 5/8. So we keep the 5/8, carry the 1. Yep, 1 and 8 is 9, and 5 is 14. So 4, carry the 1 over. 14 and 5/8. What do you think? Better than a sharp stick in the eye? For subtraction, we're going to jump right into mixed numbers. It works the same as addition. We have to have common denominators. So 8 and 3/4 minus 2 and 1/6. What's my common denominator going to be? You are correct. It is going to be 12. This is going to become 9, and this one 2. So we subtract 9/12 minus 2/12. 7/12. We keep the same name just like with addition. 8 minus 2, 6. So 6 and 7/12. Well, true to my form, it's not going to stay that simple. What's my common denominator going to be? 15. What's going to go here? 5, and here 9. We go to subtract. 5 minus 9 has an issue, doesn't it? Just like with any other subtraction, we can borrow. We borrow from this, and it becomes a 6. What's this going to become? 20. Why don't I just put a 1 in front of it? Yeah. I borrowed a whole object, and the denominator tells me how many pieces are in that whole object. So the denominator here is 15, which means I have to add 15 to the numerator. 5 plus 15, I now have 20 of those pieces. So 20 15ths. 20 minus 9 is 11 15ths. 6 minus 5 is 1. So 1 and 11 15ths. We'll do another one of those. This shows that borrowing's a little tricky. $37 and 1/4 minus 19 and 5/6. What is our common denominator going to be? 12. What's this going to become? 3/12. Good. 4 times 3, so 1 times 3. What's this going to become? 10/12. 6 times 2, so 5 times 2. We go to subtract. 3 minus 10 can't be done, so we have to borrow. This becomes a 6. What do I do to the 3? My denominator is 12, so I add 12. 15/12. So now 15 minus 10 is 5, 12, so keep the same name. Got to borrow again here. This is 2 and this is 16. 16 minus 9 is 7. 2 minus 1 is 1. 17 and 5 12s. What do you think?
Wait a second. You have to borrow, but you only added 10.
Where?
On the 37 down to 36.
Yeah.
Borrowed, you just added 10.
Well, this is a whole number though, so I just put a 1 in front of it and I borrow here.
Okay.
This isn't fractions anymore. That only applies to the denominator only applies to the fraction part.
Okay.
This is still whole numbers here, so it's still tens, powers of 10 as you go up. Yeah, the denominator only affects the fraction when you borrow. Good question though. When we multiply, let's say we got 1/4 times 2/5. We multiply the counts, which is our numerators. 1 times 2 is 2. And we multiply the names, which is our denominators. 4 times 5 is 20. Now, of course, we can see we can reduce that. Both of those can be divided by 2. Just 1/10. Now, some of you might be looking at this thinking, why didn't he cross cancel? Others right now might be wondering, what's cross canceling? Well, if we look at this, the top is going to become 1 times 2, and the bottom is going to become 4 times 5. And you might notice that the 4 and the 2 can both be divided by 2. So what cross canceling is you look at them that are diagonal, one on top, one on bottom, really. And they can both be divided by 2, so you divide by the 2. So 4 divided by 2 is 2. 2 divided by 2 is 1. And now when you multiply, 1 times 1 is 1. 2 times 5 is 10. So you basically just reduced before you multiply. Now in a problem like this one, it's about the same amount of work either way. But we can run into a problem like this one, where multiplying it out and reducing later is going to be a little tedious. For example, 24 times 35 is going to be 840. And 25 times 36 is 900. I'm sure you can see both of those can be divided by 60, right? No. You see both of them can be divided by 10. 84 over 90. You can see both of them can be divided by 2. 42 over 45. You maybe see both of them can be divided by 3. 14 over 50, right? But if we did cross canceled right away, 25 and 35 can both be divided by 5. 25 divided by 5 is 5. 35 divided by 5 is 7. 24 and 36 can both be divided by 6. 24 divided by 6 is 4. 36 divided by 6, 6. Now you might see that both of those can still be divided by 2. 4 divided by 2 is 2. 6 divided by 2 is 3. And now 2 times 7 is 14. 5 times 3 is 15. There it's a whole lot easier to reduce before we multiply. Now if you're using your calculators, it may be about the same amount of work either way, doesn't it? We're again not going to waste a lot of time multiplying simple fractions. We're going to jump up to mixed numbers. So I'm going to do something like 7 1/3 times 4 and 2/5. Well, you can multiply mixed numbers, but the process for multiplying mixed numbers is extremely difficult. In fact, if you went to any university that you chose and found 10 math majors and asked them how to multiply mixed numbers, I'd be willing to bet that not even one of them could do it correctly. So, what was the way you were taught? What were you saying? Okay. Change them into improper fractions so we don't have to deal with the mixed numbers. So this becomes how many thirds? 7 times 3 is 21, plus 1 is 22, 22 thirds. This will become how many fifths? 4 times 5 is 20, plus 2 is 22 fifths. That's strictly coincidence, by the way. Now, we could cross-cancel at this point if there was anything that canceled, but right now there's not. So, 22 times 22 is... What's that? No. 484. 3 times 5 is 15. And now we do have to go through breaking that back into a mixed number. Does 15 go in 4? Nope, so leave it blank. 15 and 48. 3 times 15 is 45. That's 3, bring down the 4. 15 into 34. 2, that's 30. There's 4 left over. 32 and 4/15. Works for me. Any questions? Anybody want to see how to do that as mixed numbers just for fun?
At that point, yeah, come up with my question.
Yep.
At that point where it was 22 thirds and 22 fifths, we could have...
If something cross-canceled, you could have cross-canceled, but nothing did here. Yeah. It's just nothing did here. Okay, so multiplying here. Remember, if we have something like 43 times 27, you have to do the 7 times 3, but also the 7 times 4. Well, same here. We have to do the 2/5 times 1/3, which is 2 times 1 is 2, 5 times 3 is 15. We also have to do the 2/5 times 7. How do I do a fraction times the whole number? We make that 7 over 1. Very good. So that's 14 over 5 times 1 is 5. So that is 2 4/5. So we're done with the 2/5. We move over to the 4. So we got to do 4 times 1/3. So again, it's 4 over 1 times 1 over 3. Is 4 thirds, or 1 1/3. And then 4 times 7, which is 28. Now we have to combine all of this. We need a common denominator. Well, we have to make them common. So that's going to be 2/15. Oh yeah, I did. 5 times 1 is 5. 5 times 3 is 15. 1 times 3 is 3. I multiplied the denominators in each step. So the 2 4/5, that's got to become 15ths. How many 15ths will that be? 5 times 3, so 4 times 3 makes 12, right? 1 1/3, I got to make that 15ths. 3 times 5, so 1 times 5 is 5. Of course, 28 doesn't have a fraction, so that's not going to change. So I've got 2 12 is 14, plus 5 is 19 15ths, which is 1 4/15. So I will keep the 4/15. Carry the 1. 1 2 is 3, plus 1 is 4, plus 8 is 12, so 2 carry the 1. 1 2 is 3. 32 4/15. Same answer I got up there. This is a lot less work. This is a very, very confusing process. I will never make you do that, so don't worry about it. It's nice to know there is a process for multiplying mixed numbers. It's just a little difficult. The biggest mistake the students will make is they will just multiply the fractions and then multiply the whole numbers and call that good. You can't do that. That don't work. That's no good. Okay, so let's do an example here again of back to doing it the conventional way. So 4 2/3 times 3 4/5. Tell me what to do. Okay, so it's 14 thirds, good. 3 times 5 is 15, plus 4 is 19 fifths. Now I could cross cancel here, but there's nothing that cancels again. So 14 times 19 is 266, I believe. 3 times 5 is 15. 266 divided by 15. 15 goes into 26 once, with 11 left over. Bring down the 16. 15 goes into 116 7 times. 7 times 15 is 105. So that's 11 left over. 17 and 11 15ths. What do you think? Good stuff? So let's do one like 4 2/3 times 2 1/4. Tell me what to do. So 10/3 times 9/4. Okay. And then 3 and 9 cross cancel, both divide by 3, giving me a 1 and 3. 3 divided by 3 is 1, 9 divided by 3 is 3. What else? 10 and 4 both divide by 2. 10 divided by 2 is 5, 4 divided by 2 is 2. So 5 times 3 is 15, 1 times 2 is 2. 2 goes into 15, 7 with 1 left over. You could have done 90 over 12, but it's a lot more work to reduce it then. So remember, you can cross cancel here at that point once they're improper fractions. Division. Yeah. This should have been 14, not 10, shouldn't it?
Yeah, I thought something about it.
That's what I get for listening to Mark. That should be a 7. So now 7 times 3 is 21. 1 times 2 is 2, so it's 10 and a half. That looks better. Or it would have been 14 times 9 is 126 over 12. No offense, Mark. Let's look at division. When we multiplied, we just multiplied straight across, right? We've said before that division follows the same rules of multiplication. So can I divide straight across? Can I do 12 divided by 4 is 3, 25 divided by 5 is 5? Can I do that? Does it work? Is that the right answer? Yeah, it is. Does it work every time? Sure does. So why don't we do it that way? Well, that's the problem. Normally we run into things like this. If we tried to do 3 divided by 2, you get 1.5. Or 4 divided by 3, you get 1 1/3, or 1.33333. It just doesn't always divide out evenly like that. So what have you been taught to do when you divide fractions? The first number doesn't change. And then
You switch the numerator and the denominator with the sign.
Okay.
Like you put a negative sign to
Kind of, yeah.
something like
Remember, the operation goes with the number that comes after it. So it's dividing goes with the 2/3. We're going to change this to multiplying by, the word is reciprocal. Reciprocal means you flip it over. Exchange the numerator and denominator, just like you said. So 2 over 3 becomes 3 over 2. And now we're multiplying. So 3 times 3 is 9. 4 times 2 is 8. 9 eighths are 1 1/8. Believe it or not, this process, multiplying by reciprocal, comes from what I did up here. Let me show you how. You don't have to write this down or anything. I'm not going to ever ask you to change how you do fractions. But once upon a time, when we did 3/4 divided by 2/3, what they would have done is this. They look at this number we're dividing by. 2 divided by 3 is reduced. 2/3 is reduced, right? So, since that cannot be reduced at all, we're going to take the numerator times the denominator. 2 times 3 is 6. We're going to use the 6 to rename this first fraction. So this is going to be 3/4 times 6 over 6. Then we're going to divide by 2/3. So what's 3 times 6? 18. 4 times 6? 24. What's 18 divided by 2? 9. What's 24 divided by 3? 8. 9 eighths, or 1 1/8. Which is exactly what we got here. You might still be wondering, well, how on earth did multiplying by a reciprocal come from this? It's not as big of a leap as you would think. Because we're looking at that, we got 3/4 times the 6 over 6, then divided by the 2/3. At some point, somebody looked at this and said, hey, if we violate our order of operations, if we stretch our order of operations just a little bit, and we do this division first, because this is multiplying by 1, it doesn't really change that number anyway. But if we do this, 6 divided by 2 is 3. 6 divided by 3 is 2. The result that we get here is always just this fraction flipped over. And then all that's left is multiplying the original number by that new fraction. So they gave this the name reciprocal and just defined division of fractions being multiplied by reciprocals. Yes, what's your question?
Where did you get the 6 over 6 from?
We did the 2 times 3 is 6, and we renamed that with 6 over 6. All I did is I left this piece out, and I wrote it as 3/4 times 6 over 6 divided by 2/3. I just took out that intermediate step. So instead of multiplying this first, I divided this piece first. Which again, the only reason you can do that is because the 6 over 6 is 1. So multiplying by 1 isn't going to change anything anyway. Otherwise, it's a serious violation of our order of operations. But like I said, somebody noticed that pattern, that because we're just going to take this number here and multiply numerator and denominator to get what we're going to use here, that if we divided that out first, we always get this fraction flipped over. So they named it a reciprocal. And they defined dividing by fractions to be multiplying by its reciprocal. Now, with that said, we're going to multiply by the reciprocal. We're not going to go through this process of renaming and dividing across. But it's interesting to know that there is a deeper process that these shortcuts come from. So now we're going to jump up to dividing mixed numbers. So we might have 4 1/3 divided by 1 5/6. Now, since we're going to change it into multiplication, it makes sense that we treat it just like multiplication and turn them into improper fractions. 4 1/3 becomes how many thirds? 13. Very good. 4 times 3 is 12 plus 1 is 13. 1 5/6 becomes 11/6. 1 times 6 is 6 plus 5 is 11. Are we multiplying now? Say no. We are still division. What do we have to do before it can become multiplication? Reciprocal. The first fraction never changes. Just like when we're adding or subtracting with negatives, the first number never changes. This becomes times, this is the one we do the reciprocal of, 6 over 11. Now what? We can reduce by a 3 there, so we get 1 and a 2. 13 times 2 is 26. 1 times 11 is 11. Which will reduce to 2 and 4/11. Goes in there twice, that's 22 with 4 left over. So what do you think? Head's about to explode?
With this and electrical, yeah.
Yeah.
We just learned about parallel circuits.
You want me to show you a key on your calculator that does wonderful things for parallel circuits? Okay, so in your book, page 32 through 33, 1 through 49, the odds. Page 41 to 45, 1 through 89, the odds. And page 49 through 52, 1 through 87, the odds. I do not expect you to go home and do 107 problems tonight.
Is that a challenge?
Well, basically, like I said before, do a couple of the easier ones, skip ahead. I mean, they're there if you need them, do them all. If you need to. If you're struggling, do them all so that you know how to do them. But if the first few make sense, skip ahead a few. Are you doing your circuits to ground, or are you still doing continuous loops?
Circuit to ground.
Circuit to ground. So yours would look like this.
Yeah.
Okay.
That's
This is parallel. This is your power right here. This is your power source. That's your battery.
Yeah.
These are your resistors. Let's say that this is R1. We're going to say is 6 ohms. R2 we're going to say is 12 ohms. It'd be easier. Now, the first thing is total resistance always has to be less than, or the equivalent resistance always has to be less than the lowest one of the parallel. Less than either of the two resistors in parallel. Think of it this way. Resistance is how hard it is to flow. So think of this, if these are pipes, right? And this is the pump pushing water through the pipe. Let's say this is a turbine or something that turns whatever. Maybe it turns a hoist or whatever it turns. So if this isn't here, so if this is blocked and the water has to go that way. Well, the water has to go through there. It pushes through there, it pushes through with a certain amount of resistance, pushing back. If I open this one up, and now it can go both ways, it doesn't matter how tough it is to go through this one. It's now still easier for the water to flow because it has more options. So even though this was the easiest one, it's still easier when I open the other one up. Total resistance. You guys have been probably given the formula 1 over R total, or 1 over R equivalent equals 1 over R1 plus 1 over R2.
We haven't been focusing on the formula too much.
Oh, you do?
Just understanding the circuitry still.
Okay.
And then we've had a couple missing classmates in the last couple days. So.
Sure. The key is a parallel circuit is what they call a current divider. The voltage is the same. Both of these are going to get 12 volts. So the voltage is constant. It's just whatever current goes here has to get split between those two. Which is called a current divider. So this actually is going to get 2 amps. This is going to get 1 amp. There's a total of 3 amps. Notice that current is split. The smaller resistance gets more current, the bigger resistance gets less current. Whereas a series circuit is what they call a voltage divider.
Yeah, we learned a voltage drop from series circuit. In a parallel circuit, each individual circuit consumes
The same voltage. Yeah. So let's say this is 12 volts here. This is 4 ohms. And this is 2 ohms. The total resistance here is 6 ohms. Just add them together, 4 plus 2. So that means our total current flowing here is 2 amps. Well, there's 2 amps here, and there's 2 amps here. There's no place for the current to split up. So the current in a series circuit, current is constant. The voltage is divided. 2 times 4, this is 8 volts. 2 times 2, this is 4 volts. The larger resistor gets more voltage. Yep. The parallel circuit, the voltage is constant, the current is divided. But it's just the opposite. The smaller resistor takes more current because it takes more current to get the same voltage with the less resistance. When you get to this formula here, there is a button on your calculator that looks like this. X negative 1. Do you have a calculator handy?
I don't know.
You do not. Okay.
But I've seen it on.
Okay. So the way you would use that is you've got 6 and 12, right? So you'd punch in 6, hit that X negative 1 button, plus 12, hit that X negative 1 button, hit equals, hit that X negative 1 button and hit equals again. Should give you 4 ohms.
What does the X negative 1 button do?
Reciprocal. That's saying this is 1 over 6. That's making that 1 over 12. Whatever I take my answer on, my answer is going to be 1 over R equivalent. So this is saying flip that back over to get R equivalent.
Okay. Okay.
It's past our time, so I gotta let you go.